Yeah. Uh, Let us start the program. So if you need Wi-Fi, this is a password that we have to connect to the guest network, the capital key. So yeah, very glad to have Sudip Jana from Max-Planck. Sudip did his PhD from Oklahoma, University of Oklahoma. And in 19, okay. Should we take a lot? I guess. In 2019, and I think he was also a visitor at Formula during his PhD. And after that, now he's a postdoc at Max-Planck in Heidelberg. So he has been working a lot in various model building and phenomenology of neutrinos. And he'll give a series of lectures on neutrinos. So I think today is more like historical perspective. Okay. Please.
Thank you, Singh, for introduction and also for giving me the opportunity to talk about the neutrinos and some of my works. I'll give some lectures on it. So my lecture will consist three aspects will be there. In the first lecture, I'll tell about how different problems arises in neutrino sector, what is the historical development, how it has been done, and how it was solved. And then second lecture, maybe it will be a bit technical, where I will try to teach you how to write down from some guess theory, how to write down neutrino mass models, or how to construct like defined mechanism like seesaw or radiative mechanism and so on. And third lecture, I'm planning to tell about neutrinos new interaction. It can be neutrinos electromagnetic interaction or neutrinos non-standard interaction. So this is kind of structure, but depending on how I'm proceeding, like I'll talk about these things. Since the audience is diverse, like before going to let's see what is neutrinos. Of course, all of you know, but like what first from galaxy, you see that if you zoom in and in, suppose the early 18th century, it was considered that the atom is the smallest indivisible particles. But then in 1897, which I'll talk about it later, that this is the scale of the nature. If you see, the pointer is not. Okay, it's not working. No. This is too bright.
Not show on the script though.
Okay, anyway, so here just I'm showing that different scaling. As you can see, the human scale, which is around 1 meter, and if you zoom in and in, you will end up with subatomic particle. And so far, our understanding was in standard model, which consists of 17 fundamental particles or elementary particles, as you can see on the left. 6 quarks, 6 leptons, 4 ghost carrier for strong electromagnetic and weak forces, and there is Higgs boson. And I'll talk about neutrinos. As you see, the 3 fundamental particle among the 17, and what sort of new physics or what sort of things we can learn from this neutrino, because these are among a handful of non-fundamental particles. So then the next question is from where neutrinos can come from. Neutrinos are the second most abundant particle in our universe, as you know. For example, the sun, if you put your hand in per second, almost like 100 billion neutrinos are passing through. So the sun is an excellent factory of neutrinos, and there are other sources like supernova. Also in accelerator, you can produce these neutrinos. Here I am summarizing that the neutrinos, like information for neutrinos comes from like different 25 orders of magnitude in energy. If you see the energy scale and the cross section and different experiments, the solar experiment, different experiments also I am putting there. For different sources, there are different experiments are ongoing. So this is just briefly, I'm summarizing the sources. Even if you can think of banana, like where you can produce millions of neutrinos per day. So because this is also due to radioactivity and so on. So neutrinos are everywhere. Then this is one interesting slide which I thought I should put, like the timeline of particle discovery, how different generations of like elementary particles were discovered, when do we know like 3 species of neutrino or 2 species of neutrinos and so on. If you look at the time scale, nowadays we got very impatient very quickly, okay, there are not much discovery. But if you look at the timeline, each 10 years, even if in some of the 10 years there are no discovery. If you see, like this is one interesting slide that 1897, when the electron was discovered, that's all the green colors are the charged electrons discovery timeline I'm showing. And the purple ones, which I'm putting defined force carrier. As you see, there are defined like a huge gap between these timelines. And in 2012, the last one, which is Higgs boson, which was discovered among the 70 fundamental particles. You see, it's bit scattered. In each 10 years, there could be one discovery and so on. We need to look for, we need to be patient and.
People on Zoom cannot hear well. So, I think she can give cái tàu cái như tàu cái kiểu
Stick or something, we should point them. You have some sticks or something which I can point out. If not, oh, okay, I see. Okay, maybe I should continue.
then you should continue.
Okay, so here just I'm showing that defined first elementary particle discovery happened, which is in happened in 1897. So then muon and tau, and if you see the neutrino, it's around this 1950s, 1960s. During that time, electron neutrino, then muon neutrino, and tau neutrino in 2000s. And in 2012, like it's boson discovery, all these elementary particles which I showed. So if you see the timeline, like there are lots of gaps. Always you need to keep patience. Like we cannot expect that this sort of discovery on regular basis. So you need to work on it. So let's see, before we are going to detail, like when is the, like how the neutrino postulation started and what leads to this type of neutrino hypothesis and how we discover different generation of neutrinos. So first, let's take a look of late 19th century. in 1896, basically, Henry Becquerel, one French physicist, like who was very curious about this fluorescence material. You take some uranium or any fluorescent material exposed to light in the outside, then you take back in the lab. During those days, there are no labs. So you keep it in office and we put it in photographic plate, then it puts some uh, radiations, or sorry, it puts some line on the photographic plates. From there, you study these phosphorescence and in past, if you see, a lot of discovery happens by accident. That's what I was just showing. In this case, also similar thing happens. In Paris, it was like rainy day, and there was no light, and he was supposed to be going for vacation. So he did not expose on the light this material. So there was no stimulus. So we should not expect. So he put that uranium material inside the drawer. But when he come back after 2 weeks, he found some lines on it. And it leads to the discovery of radioactivity because it is not normal. You do not like stimulate by any other things, but you are still getting some. It's fine. Just so it leads to this radioactivity, and after that, why I'm telling about radioactivity, because it is very important to which leads to discovery of neutrinos. So after that, this Henry Becquerel's work, Marie Curie was so motivated. Her PhD thesis was on radioactivity, and then her husband, Pierre Curie, was working on magnetism, abandoned that to join working on radioactivity, and this trio got Nobel Prize in 1903 due to this radioactivity, and this was also by accident. So then it is very important when we talk about radioactivity, we know nowadays we know that there are different kind of like radiation, alpha, beta, gamma, all these radiations are there. They have different characteristics. But it is important to know that the next year in 1897, J.J. Thomson in Cambridge, like during that time he discovered electron. It was very important during that time because all this radioactivity, what I will tell later, like in beta decay and beta, what it consists of, what it looks like. This elementary particle discovery like opens a new avenue because until then, people are believing that the atoms are the like most fundamental particle. You cannot like divide it. This experiment, I think all of you are aware of. So I'm not telling detail, but it's an interesting experiment. What he did, like this in cathode ray tube experiment, if you see, the cathode ray comes out, but if you have some kind of cathode and anode, it's attracted towards anode. And then if you put some electric plate, it was always getting deflected. Okay. So from this deflection, you can see this radius of curvature. And if you devise such a way that if you impose electric and magnetic field, which consists out, you can calculate Q over M ratio. It was interesting to know actually. Let me write it down. So it is interesting that suppose say the electrons are like the cathode ray is going this direction, it's X direction. And if you have magnetic field towards this direction, then it will be deflected and you will have some force. And this is a very interesting ratio because so far we know about this ratio, charge over mass ratio from hydrogen atom. And what J.J. Thomson found that this Q over M ratio is 1800 times larger than this Q over M hydrogen atom. Okay, so what does that mean? And also, like, it was electrically like negative particle. And so you can see either you can say that, okay, Q is 1800 times larger. We are finding some particle which is 1800 times like more charged than the hydrogen, or the mass is 1800 times smaller. Okay, that leads to this this famous experiment leads to this fundamental particle discovery by J.J. Thomson, and later he got Nobel Prize in 1906 for this work. And then it comes to 20th century. So this is the end, which like started all these developments of radioactivity and so on. And nuclear physics during those times were like quite popular. So as I mentioned, in the early 1900s, detailed analysis of this natural radioactivity revealed that different elements emitted different types of radiation, say alpha, beta, gamma. And all these three radiations are sensitive to three different forces. If you see alpha strong, beta weak, and gamma electromagnetic. And they have different characteristics. For alpha and gamma, it was quite not so troublesome, but beta spectrum identification was quite tough during those days. So in 1914, actually Sudip, using very advanced technique, he proved that like the beta ray spectrum was continuous. I'll show you, which leads to Pauli postulate the neutrinos hypothesis. So it took almost like 15 years after Sudip's discovery that experimental issue was settled, because in some experiments, this beta ray spectrum, they are finding some discrete spectrum, and Sudip settled this issue, and he found like this beta ray continuous spectrum. Even if when this discrete spectrum was found, like it was so dramatic, like during those days, people are trying to give up the principle of conservation of energy. And in 1929 and 1930, Niels Bohr contemplated the possibility that nuclear electrons not only did not behave as ordinary fermion, but also interacted in a way that violated energy and momentum conservation. Okay, because your beta ray spectrum supposed to be discrete, but they are finding continuous. So that leads to say that, okay, since it is not following the energy and momentum conservation, maybe that principle is violated. So that was the desperate solution which people are trying to contemplate during those times. Then the neutrino enters into the like the thing that like so as you see on the diagram, in the beta ray spectrum, emitted beta, like this energy, if you see energy distribution, this is continuous. If suppose there is no neutrino, like this way, then I should expect a discrete energy here. But what we are finding, like kind of a continuous spectrum, and this leads to the postulation of neutrino by Pauli in 1930. And there was a conference in Germany in Tübingen for the experimental physicists. And he sent a letter to President, and where he is addressing by saying that, dear radioactive ladies and gentlemen, I have done a terrible thing. I have postulated a particle that cannot be detected. There are many interesting philosophical statements out there, even if like in his letter, he's mentioning about neutrino can have mass and have like, he called it neutron in his letters. This is the original letter is in German, but later it's translated into English. You can find in literature. So that's the first time the neutrino was postulated to explain the beta ray spectrum. That if neutrinos also carry out some energy, then you can explain this continuous distribution of this energy spectrum. And later Enrico Fermi was able to demonstrate this elegant theory of weak particle interaction that included in the neutrino. And this is the English version of it. As you can see, in between somewhere he hesitant, like he was writing I do not feel secure enough to publish anything about this idea. So I first turn confidently to you, dear radioactives, with the question as to the situation concerning experimental proof of such a neutron. Neutron is not the neutron. Neutron, rather, here he is mentioning about the neutrino. So also there are some debates about it that he was not confident enough or he was afraid to present this, but Pauli is Pauli, so it's yeah. So that's the story. That's the how this neutrinos postulation. I will tell chronologically to give an overview of this neutrinos development, how happens. So in 1930, as I said, Pauli first postulated to resolve the problem of continuous ray beta spectrum and to reconcile nuclear model with spin statistics theorem. Then in 1932, also it's important, Chadwick discovered the neutron, the neutrinos nomenclature, how it comes. The neutron, it was interviewed to like Fermi in an Italian conference, I think. So then he was telling like, tell about this neutrons discovery. So then Fermi basically was saying that, oh, this is not the neutron which was postulated by Pauli, this is little neutron. And if you translate into Italian, it's called neutrino. And the same nomenclature still persists in supersymmetric many particles, chargino, Higgsino, that means all smaller versions of this. So that's how the nomenclature comes. But he only did not give the nomenclature, but like in 1934, the famous work he has done, which was quite important to understand this, the Fermi theory of weak interaction. He write down the current interaction, as I showed in the slides. As you can see, you can write down like this type of, like nowadays you write down 4 Fermi interactions. Similarly, you can write down electron neutrino and proton neutron, like this type of interaction, and this form can be anything. Like it can be vector, scalar, and all type of things it can be. But whenever this theory has been developed, then you can compute the processes like this type of interaction processes cross-section. And it was found to be so negligible, even if Pauli did some bet, that we will never be able to detect such neutrinos. And by the way, I should mention that these proton, neutron, still these are considered that to be elementary particle during those days. Quarks and other things discovered pretty much later. Then, if you see the timeline, in the 1935, Yukawa postulates the existence of, like, if you see this type of interaction, so basically, so this type of interaction, like basically Fermi proposed, and then, but it was like kind of, we don't know the force failure. That's how I'm writing current interaction. But Yukawa proposed that existence of some force carrier for the strong interaction, which holds neutron and proton together. So, and this force mediator, you can basically calculate the corresponding mass, what can be the mediator from its nature, from the range of the strong force, and which he postulated like pion mass, which needs to be around 100 MeV, which was very interesting when we postulated that next year in 1937, there was another particle discovered, which is exactly like 100 MeV. It was like this for the first, imagine that like you propose some particle which you expect it to be at 100 MeV, and next year you are finding a particle which mass is exactly around 100 MeV. So people are puzzled by this and first thought about that this is the same pion which was Yukawa proposed. But there was some issue on it. Like this type of pion discovery happened, like if you have cosmic ray hitting almost like 50 kilometers above this pion, so it should be like, if it is like effective to the strong interaction, it should immediately decay. but it's decay a longer path, and then you are detecting these muons. So that must be some different long-lived particle coming from the this cosmic ray and so on. So then the Max-Planck and Bethe propose that, oh, maybe it's not pion, but pion decaying to some particle spontaneously, and that is much more long-lived and which we are detecting now. So that was the hypothesis. This type of hypothesis, we nowadays any anomaly appears or anything, we like always talks about this, so that but they are also like afraid that this type of like new particle extension, like they are conservative about it, but later turns out to be that's the thing which is happening. Pion that decaying to muon, so they found a second generation lepton. But even if after muon discovery also, when Anderson and Nadelmeier made this groundbreaking observation, even if people are thinking muon may be some kind of electrons excited state, like maybe not second family. So when we get to know about this two neutrino hypothesis, I'm coming into the next slides. So then interesting thing happens. This after this 1930, like 47 and so on, and during this time, sadly, like there was different nuclear bomb testings, and this Manhattan project was going. So then Renes, using this idea that since nuclear bomb, whenever it explodes, you have lots of neutrinos are coming out. What about if your flux is too high, there will be like huge probability to get this neutrino may be detected. That's why this is the first proposal came from the Renes, that this is the nuclear bomb. If it explodes, you will put a detector like fish lights. Whenever it will detect, there will be lots of neutrino coming in, and it will fall, and there will be feathers and foam where this detector can be stored. That was the first proposal to look for this neutrino, how to detect it. But this was never like approved, due to the fact that you see there is a possibility of like, because it is very close to this explosive. So this is not viable, maybe like this detector can blown out. So then the next, this was not approved. Then the project which is called, I'll talk about it. So instead of nuclear explosions, like they said that, okay, maybe what about nuclear reactor? Nuclear reactor also we can get a lot of flux, and that's it's called Project Poltergeist. You can look into these details in YouTube or any other places. There are many interesting stories about it. And that's the proposal, first proposal comes how to detect neutrinos, like using inverse beta decay, particularly this process. There are many ways you can, with cost symmetry, you can write down these equations. Basically, what you will do from the nuclear reactor, lots of anti-neutrino coming in, and as you can see in the diagram, it hits the target, this proton, and you will produce positron and a neutron. And if you see the detector, because you need also gigantic detector to detect these neutrinos. So you have a 3-layer. These are the 3 layers I'm showing. But it's also not so easy to detect these type of events. Whenever you say you produce positron, basically you look at the gamma. Like after annihilation, like this positron annihilation, this gamma, you look in the liquid scintillator detector and you detect this gamma. And how do you detect these free neutrons? These, like due to a particular characteristics feature, you can detect these events. So these free neutrons are very hot. Before it got captured, it's like goes through many interaction, and then it got captured. And also that emits a radiation, photon. So there is a like time gap, characteristics time gap between these from the positron, the photon, the gamma you are detecting, and from the neutron. And by looking at this, you can say that you detected these type of events. So due to this characteristics time gap, actually it was easier to get this neutrino to be detected. And as you can see, in 1953, scattering events was obtained in 1953. And in 1956, definitive and evidence was only obtained in 1956. And the final results were presented in 1960 with a larger detector next to Savannah River reactor site. And that's the first time we see some, better to say, anti-neutrino events. And due to this, 1995, Linus was awarded the Physics Nobel Prize for pioneering its pivotal contribution to electron physics. And if you see, this is the letter to Professor Pauli, who said that these neutrinos will never be detected. So that's the letter from Renes that we are happy to inform you that we have definitely detected the neutrinos from fission fragments by observing inverse beta. So he lose the bet, but he must be happy that the neutrino was detected. And that was the development during those times in 1956. Until then, like the first time neutrino was detected or anti-neutrino was detected. But there was another interesting discovery happened in late 1950, 1958, this famous Goldhaber experiment. So this experiment was trying to look for a neutrino polarized, like a neutrino whether left-handed or right-handed. So this Goldhaber experiment, what they do, electron capture with europium, and then you like get some excited samarium which decays and leads to photon. And from the conservation of angular momentum, you can correlate the neutrino helicity to the photon polarization. And then these experiments claim that like 100% these neutrinos are polarized, like as left-handed. So this was a crucial, like I will say, this is very important during those days, that to know that neutrinos are left-handed, like 100% times as they claim. And then the interesting story happens. Let me tell you that. So when we get to know that there are second generation or like second family exists, like, okay, we discovered muon, but people still are puzzled, like it can be some excited state of electron and so on. But as I said, write it down. Okay. So still that time we don't know about, we do not have good structure, like whether there is two generation or not. Like we discovered muon and we detected one species of like neutrinos, basically whatever we are getting in reactors. So then this is the following thing happens. So you know these type of interactions you are writing from pion decay, whatever the this pion decays to muon and then muon further decays, and this is the decay process. But if you can connect these two, and then it leads to some mu to E gamma processes. For the moment, just don't think about different lepton numbers. Say, suppose say this is same neutrino and same anti-neutrino. Okay. So then you can connect these two diagrams and it will lead to mu to E gamma process. And if you compute that, you will get that this branching ratio of mu to E gamma will be 10 to the power minus 4. But it was measured like it's not so people are not getting such processes in mu to E gamma. So then the two neutrino hypothesis comes. Why? Because if there is no mu to E gamma happens, so then how I can suppress this? So then the new lepton number was introduced. So this neutrino and this neutrino are not same like lepton number. So then the new lepton number which is introduced, muon lepton number. So if you have like one species of neutrino has electron lepton number and one species have muon lepton number, this you cannot do. And then it's very suppressed and which is consistent. And you know that current this type of limits, branching ratio mu to E gamma is kind of 10 to the power minus 12, say roughly to say, by make collaboration limit and so on. So this is the time when it leads to think about why like this two generation hypothesis or the two neutrino hypothesis started like developing. So whenever like this type of idea was very getting interesting, so Liederman, Schwarz and Steinberger, they try to look in the accelerator neutrino. If you have two generation, if you have associated neutrino with muon also, then they should look for it wherever say pion decays. So then they look for from the accelerator, as I showed you, here's some cartoon diagram. You have booster beam, it hits target, and then it produces a lot of pions, and pions can decay to nu mu or nu mu bar. And you can, in the detector, you can detect these different new species of neutrinos. And that's how like they detected the muon type of neutrino, and you see the Liederman. So it leads to the second neutrino discovery, which is like after electron neutrino, you like not electron neutrino, better to say anti-neutrino discovery, then this muon neutrino was discovered. So far we discovered two neutrinos. And then, as I said in the beginning, like sun was very interesting during the like studying sun or studying stars in astrophysics. Lot of development was happening during that time. So people are curious about what is happening in sun, how this nuclear fusion works, and so on, so on. So Hans Bethe, in 1930, actually, basically, if you go back a bit, in 1938, there was one conference happening for the astronomers and physicists. There he got the question, how stars shine. And it led him to think about all these reactions which we write down nowadays for the nuclear fusion. Basically, it was by Hans Bethe who clearly write down all these possible equations, how this fusion works. And he received the 1967 Nobel Prize in Physics for revealing how the sun behaves like a giant nuclear reactor to produce the vast amount of heat and light that supports life on Earth. But one thing he did not do, in his all equations, he never write down neutrinos. So then John Bacall, in his one statement, he is writing that Hans did not bother to include the neutrinos in the equations that he wrote for the nuclear fusion reactions. He must have thought that neutrinos are so elusive as to not be worth mentioning explicitly. So that was the case. So like sun, as it was mentioned also, sun's kind of gigantic nuclear reactor, where you can produce a lot of neutrinos, but he just ignored it, like because maybe some light elusive particle and so on. That's where the solar neutrino whole story starts. Then John Bacall, like he was theorist, and Ray Davis was a chemist actually. And then he discussed with Ray that how to look for these neutrinos from the sun. And then in Homestake mine experiment in South Dakota, the idea was that using the mine, which was out of gold, like there you put lot of chlorine, and chlorine was very cheap during those days. You can buy it. And with this chlorine, like whenever the solar neutrino from the sun coming in and hitting this chlorine, it can transform into argon and electron. Anybody have any idea like how what should be my search strategy, to look for electron or to look for argon? Or Ray Davis, whenever first saw the solar neutrino, what they look for, so that they can say that they found some solar neutrinos. Actually, nowadays electron identification is much easier, like if you say, but it was not the case for their scenario. They are looking at argons, because you have a like huge mine, like a chlorine chamber, where like you can filter out these chlorines, and argon is noble gas. It's not basically interacting at all, so it is just sitting there, and it's an enormous like effort you need to put to take the filter out of the chlorine, and then you can count basically how much argon are left. And from there, you are basically say that like this neutrino you detect. And when they try to look for the solar neutrino, what they expected, they found 1/3 of it. And this is called famous solar neutrino, like this is part of the solar neutrino problem, which we are aware of. And Ray Davis and John Bacall, although this experiment started around 60s, and they try to figure out this how to detect the solar neutrino. And in one place, I read this statement that what a doctor does when he or she uses X-rays to see what is happening inside our bodies. So similar to that, we can look what is happening in the sun by looking at the neutrinos. So that's the proposal basically two of them developed. And like as I said, when they detect the solar neutrino, they found like almost like 2/3 deficit. And this is one interesting slide. As I showed you in sun, there are different reactions happening, and these are called different neutrinos. Suppose say these are in PP fusion, it happens, you call PP neutrinos. Then also there are other processes like PEP neutrinos. So all these processes can like at the end product, like you are getting some solar neutrinos, but in different energy range. So that's what I'm showing here. If you see the neutrino energy, and different processes produces different type of neutrino energy range. PP neutrinos energy is smaller, much smaller. So, and different experiment was targeting for like different energy range. So chlorine experiment sensitivity was like almost like above in 1 MeV and so on. And you can see up to 10 MeV, mostly you can detect the solar neutrinos. And similar to the chlorine experiment, there was another experiment later was like gallium experiment and so on. And they look for much lower energy where you can look for this PP. But here you are looking for boron neutrinos, and there are other neutrinos there. So now, what was the summary then, like during this development, like for the solar neutrino? Here I am showing you these things. So this was the chlorine experiment. The expectation was like here with some normalization factor, but they found like almost like 1/3 of that. Okay. So then other experiment like Galax and Sage, all these experiments, if you see that in all experiments, they had some significant deficit. So like Homestake, Kamiokande, Galax, Sage, all these experiments found this deficit of the solar neutrinos. But later I will explain it. Like in Snow experiment, whenever they look for all neutrinos, that is matching with the solar neutrino flux expectation. Okay. So, but in other cases, every like only if you consider nu E, like there was a significant deficit there. So one thing here to mention also, this is kind of which I find very interesting. When the solar neutrino problem arises, like their community was kind of divided into 3 categories. People say that, like one who was not believing Ray because he's a chemist, he cannot do physics experiment, or like this experiment is crazy, you may be detecting something wrong, or the precision is not so high. The second part of the community who are like who believes that John Bacall did some, okay, he messed up with Bethes equation. I think these are so complicated, you don't know what is happening in the sun. So Bacall was wrong. And the third sector of the community which believes that both of them are wrong. So there was no basically any people like who are supporting these, that these are to be correct. So then in Caltech, actually first Ray Davis presented his result, and where Ray presented the result, actually Bacall was quite upset, and he's writing in his statement that when Ray first presented his experimental results at a small private seminar at Caltech, I was very depressed. I did not have tenure, and my most widely discussed prediction had just been shown to be wrong, although nobody proved that. So, but like because of the so much propaganda and other things, people believe that these type of problems are not so interesting problem. People should work on something else rather than detecting these elusive particles and these solar neutrino. Then Nick Feynman saw how discouraged I was and took me for a long walk to encourage me. How he said that I should not feel badly because no one had shown that there was an error in my calculation. This walk at a very critical time in my life is an example of the importance of the human element in science. Please never forget the great importance of human element in doing science. So it's quite interesting. And like, even if nowadays, if you do physics, if you are doing research, if you're thinking something new, you can be discouraged by many people, n number of people. But you need few good friends who can this is one prime example where he was discouraged for like most of the time that this is completely wrong, this cannot be correct. Now hundreds of experiments which is looking for the same things and still establishing the what they have observed. So it's a kind of a lesson. So that's why I just mentioned that. And then Nobel Prize in Physics 2002 for pioneering contribution to astrophysics, in particular for the detection of cosmic neutrinos. But then the question is, like all these in solar neutrino, you found some deficit, but like where this comes from, this missing neutrinos. So then it was popularly known as solar neutrino problem. And then people are proposing different kind of hypotheses. What can be the reason why this? Of course, one reason I already told, like everybody is wrong. So experiments done did the right things and so on. That was one hypothesis. But let's take a look, like what are the hypotheses during that time people come up with. So first thing was very funny, like I found in this Claude Frank's book, that sun might be burned out, there are some ice age coming and so on because you are finding some 2/3 deficit. So it's a crazy way of writing, but in a book, it was written like that during that. The second solution, which was interesting, I should mention that Pontecorvo in 1950, there are two papers in 56 and 57. In the first idea of neutrino oscillation was put forward by Pontecorvo in these 56 and 57. Interestingly, in the 56 paper, he talks about neutrino to anti-neutrino oscillation. And in the 57 paper, he talks about neutrino oscillation. Anybody has any idea like why in 56 somebody is talking about oscillation? Because of the
chaos system?
Not really, although that was in their mind, but like there was no experiment, nothing, like only you just detected in 54 or so, just only reactor antineutrinos. So if you cannot think of, even if like any oscillations or anything, like people still not settled with muon neutrinos and so on. The reason Pontecorvo wrote because you see, like there was nothing about neutrino oscillation. Suddenly in 56, 57, there are two papers, and then there was no discussion. Then again, solar neutrino problem arises in late 80s. Suddenly again, the discussion started. It's interesting to know. The reason is that I was talking to Alexei, and he confirmed this fact that when Renes was trying to look for first detect the neutrino, that time Ray Davis was also trying to do the same thing, to detect the reactor antineutrino, but with chlorine. And he did not find anything, because that was also a good lesson we can learn from that, that is the time we realized that neutrino and antineutrino are different, because and in his whenever he took the data for Ray Davis, just in 56 or so, he was motivated by this Renes experiment. He was trying to look for that, and he found some data fluctuation. And then the conference happens, and in an informal chat, Pontecorvo was informed about this fact that there are some kind of fluctuation happening to like looking for neutrino and anti-neutrino events. Like Ray was doing some experiment with chlorine, and he finds some weird events, but that is not consistent with the other things, and it was never published. But he was so motivated. Okay, what can happen if suppose say some neutrino oscillates to some anti-neutrino or something like that? So like if you have some sterile state, so active neutrino can oscillate to some sterile state. Like those are the ideas, first ideas of, that's why that time neutrino oscillation was put forward by Pontecorvo in 56, 57 and developed after the following decades. So in a standard model interaction, a neutrino of one type is produced while traveling, it changes its flavor and can even become another type of neutrino. These yeah.
What fluctuation was the fluctuation what the energy or
Yeah, so fluctuation in this excited atom, the argon. He was looking for chlorine plus some new yeah, yeah. And that's the reason he this whole oscillation idea was, because that time solar neutrino problem or nothing was there. It's a 57. So that leads him to think about if neutrino oscillates, what could happen. This was quite interesting, but then taking his proposal, people are writing like this, there was like 2/3 of deficit. People thought from sun, all these electron neutrino you are producing, and it is oscillating to the some sterile neutrino using this theory. And then you can explain the deficit, but it was a like almost it took a decades why it is not the correct prescription. Later I will talk about this MSW resonance and how it explain it. But that was also one hypothesis. Then third one was like, okay, maybe neutrinos have a finite lifetime. All these electron neutrinos are coming in, on the way it's decay to some other state or something like that. So that was another hypothesis. So I'm just highlighting flashing the main hypothesis, like different people proposes different ideas in the early 90s and what sort of ideas they put to explain this deficit of these solar neutrinos. Then also some people proposed this is considered to be the second best solution. Even if best solution during those days people considered until the Snow-Cumberland result. If you see Homestake mine experiment result, like this Ray Davis experiment, there was some time anti-correlation and in sunspot activity in chlorine experiment. And then people propose that maybe the neutrino has some magnetic moment, because if you have a massive particle, it leads to some non-zero magnetic moment, and sun has magnetic field. So you have a spin flip transition, and that is leading to like nu when it is coming out, it is going to some other state, and that's how you can explain the deficit. And this was fitting so well this the data. Ray believed that this was the explanation. Even if in his Homestake mine experiment, he never cited the MSW solution due to that, because this solution they thought like this is the solution which is happening. And of course, there are many crazy ideas, but like one of them was also like violation of equivalence principle, violation of unitary evolution of quantum mechanical states, Lorentz violation, like violation of Lorentz invariance and so on. I'm not going in detail. Of course, the other solution was that neutrinos change flavor while they propagate, and the solar anomaly required this survival probability of electron neutrino to be less than 1, while I'll talk about this atmospheric anomaly also, which required also muon neutrino survival probability less than 1. So this was quite consistent picture for the like oscillation could explain this type of phenomena. But then like later we realized that MSW and other things you need to take into account. Briefly, let's talk about the scene side. So these are the solutions 7 or 8, which are quite popular. People are playing with it, how to test these hypotheses and so on. So out of which 2 are very like concrete and that was neutrino magnetic moment hypothesis and the oscillation like oscillation things. And during those time, this late 80s and early 90s, another thing happened, atmospheric neutrino anomaly appears. What was that? So unlike the solar neutrino flux, where you can measure it so precisely, atmospheric flux you cannot measure precisely. There are a lot of uncertainties and so on. So people try to figure out experimentally, like what are the characteristics, some say observable, which I can look for, which I can measure very precisely. That they define as R ratio. And this R ratio is defined to be measured beyond type to electron type flux of the neutrino divided by its theoretical prediction. And during those times, there are 2 types of detector which are detecting these atmospheric neutrino. Atmospheric neutrino, you already understand what I was saying, like cosmic rays are coming in, hitting the atmosphere, say 50 kilometer above, and when they produce this pion decay, and you can get these neutrinos, and you see you can get new type of events as well as new muons, so you can define the R ratio. Interestingly, there are 2 types of detector, water Cherenkov and iron calorimeter, and I show the timeline. All water Cherenkov detectors are finding this R ratio to be less than 1, and all the iron calorimeter detectors somehow getting this ratio to be 1. This was quite puzzling. This is the starting of atmospheric neutrino anomaly. Like if you see the number, these are the defined experiment. This water Cherenkov and other experiment, as you can see, like these are disagreeing with each other. And Super-Kamiokande also find this type of discrepancy with the iron calorimeter and so on. But there was one interesting fact about Super-Kamiokande that I did not tell about Kamiokande. Like basically, Kamioka is a village in Japan, and NDE its name is not just random. NDE means nucleon decay experiment. So in the Kamioka village nucleon decay experiment, during those days, grand unified theory was quite popular, and people are expecting some proton decay events they could observe and so on. So this experiment was built. And Super-Kamiokande means they did something better than the Kamiokande, of course. So Super-Kamiokande has some precision other than the measuring R ratio. Unlike the other experiments, they have one thing better. They can look for from which direction these neutrinos are coming. So directionality. And what they found, it was interesting, that suppose you have detector here, these are supposed to say, let's call it downgoing, or this is upgoing. So then it was supposed to be like, if you consider this flux to be isotropic, then I should expect upgoing and downgoing events should be 1 for the atmospheric neutrinos. But they found it's like less than 1 and it's 0.54. And people don't know why. And if you see the error bar, it's quite small. And this is measured with like more than 10 sigma significance and so on. So then, and also this is the data, as you see, and this is one picture of Kamioka. If you look at this data carefully, you will see that electron-like events, it was quite matching, but for muon-like events, these are the zenith angles. If you go from 0 to -1, this observed data was quite different from the expected flux. Whereas for the from 0 to 1, this was quite matching. So in the muon events, how it can be so consistent, or for the electron-like events, for the muon events like upgoing and downgoing, for each cases it gives a like huge discrepancy. And that also, like, then it appears this atmospheric neutrino anomaly, like how to address this during the same time. then people are doing same hypothesis, similar type of hypothesis that from the downgoing muon, like for the neutrinos coming in, that may be decaying. That's why, like, due to this finite lifetime, it can explain these upgoing and downgoing events, because there you are traveling very short distance and you cannot decay. Then, of course, as I said, this neutrino changes flavor while they propagate. That means if new mu is coming in, if it gets enough distance, it's oscillating to other flavor. So that's why you are getting deficit, because through the earth you are traveling more distance. So that was a very good explanation during that time. So how much time I left? Half an hour. Half an hour, okay. So maybe we can, yeah. So these are the hypotheses during those days for. Sorry. Okay, I'll try to wrap it up. Maybe now, because there are many information I shared. Maybe tomorrow I'll talk about some detail and some technical solutions like MSW effect and other things. That will be better, because today I think I gave too much information. Okay, so just I'm giving you the context, like that's how, like, as I started from 1896 and we are now in like late 90s, like what is the problem, how this neutrino becomes a completely new, like, huge field, and people are working on different problems, and it's so much puzzling. Several anomaly appears, goes away, and some are established and so on. So then the last thing which was like, here I'm showing the current knowledge of neutrino oscillation. Basically, like, currently now hundreds of experiments has established that fact, right? So you produce these neutrinos in weak eigenstate, and if you give enough distance, you are propagating in mass eigenstate, and after a while, like, it oscillates to other flavors. And you can write down the flavor eigenstate in terms of mass eigenstate like this way. And you know this, due to this discovery of neutrino oscillation, Kajita and McDonald got Nobel Prize. Neutrino masses are non-zero, and the standard model cannot explain this. Let me explain a bit the data. Okay, in the two neutrino hypothesis, as I said, when you have two neutrino hypothesis, like, you can write down always these two neutrino flavor eigenstate as a linear combination of two mass eigenstate, and then you compute the oscillation probability, and you can write down in terms of mixing and mass splitting, and it depends on the length and the energy of the neutrino that you can write it down. So here I am showing that say electron neutrino, if you start with say some probability 1, and if it travels certain distance, then due to this oscillation, like, it will change into different flavors, and so you can get non-zero probability of other flavors. Let's try to explain this atmospheric neutrino anomaly via this thing. So if you see, like, P mu mu oscillation probability, you can write down, like, say in the two neutrino framework, you can write down the muon neutrino survival probability. Muon neutrino survival probability, the expression I write down here. So now you see if sine square 2 theta is almost like 1, delta m square is 10 to the minus TV square, you will find like this oscillation probability for that particular region, like almost like 1. But here oscillation goes so fast, like you will get like 1 minus half sine square 2 theta. You can work out, and you will expect that from this oscillation, like, you can expect this, if you consider this oscillation hypothesis, then you expect this type of spectrum which can explain the data. And for the other cases, for the electron-like and events and so on, it will be unaltered. So that's very well fitted with the atmospheric neutrino problem. So the basically you start with nu mu and then over the distance, like it's oscillates to different flavors. So then different experiments comes and confirms also this type of hypothesis. Just I'm mentioning those names K2K, Minos, Opera, all are basically observing similar sort of events. So it's basically slowly like people started converging on this viewpoint that due to oscillation, these are the things happening. And now many experiments have proved that. And now I will briefly talk about maybe the MSW effect, the addressing the solar neutrino problem. Although I said that like oscillation explains the atmospheric neutrino problem, but for the solar neutrino, it is not the case. It's not oscillation can only explain this phenomena. There are certain things you need to take into account, these MSW effects, which I will explain now. Before going to that, we should know that neutrino, how it interacts. Neutrino in standard model, these are the two type of interaction, you can write it down. The electron is something special. As you see here, because matter consists of electron, you can only write down here nu e because the charge current is flavor diagonal. So here you can only write down nu e. But for the neutral current interaction, you can swap any flavor, and that basically it's kind of universal to all the flavors. So what does that do? That do coherent forward scattering of nu e of electron in matters generates a matter potential. And in solar core, this is like around square root 2 GFNE, which is around 8.2 times 10 to the minus 12 electron volt in solar core. It's a very small number, but if you multiply it by energy of the neutrino, you will see that exactly it's equivalent to delta m square. So energy of 10 MeV, if you multiply with that, you will see that particularly that will be equivalent to delta m square. So due to these special cases, which modify the diffractive index of nu e and neutral current interaction is universal. These ideas are first like this thing was proposed by Wolfenstein, and then McCabe and Smirnov gives this non-trivial solution to this solar neutrino problem, which is quite interesting to know. So what is matter effect or this MSW effect whenever I am talking about? So whenever you do like neutrino propagation equation, you can write down like in terms of like this in the flavor eigenstate, you can write down like this way. And as you see, like there should be a new term in the ultra relativistic limit, like due to the like because in sun your matter density is too high, it should change the dispersion relation. So that you need to take into account. So basically you start with the Fermi-Lagrange, and after a few rearrangement of the charge current terms, you can write down this type of interaction. These are the called as you know, like these are popularly known as 4 Fermi interactions. So you can write it down in terms of neutral current interaction, and that will affect in the oscillation. And equation of motion for one electron neutrino state in the presence of a non-relativistic electron background, you can write in the rest frame of the electrons like this. And then Dirac equation for a one neutrino state inside a cold electron gas, you can write down following this equation. And then you can write down for the dispersion relation, then E is not exactly this P, but it's corrected by square root 2 G at NE. So then it's interesting to see there will be two matrix. So whenever you consider neutrino propagation, like you start with a neutrino flavor eigenstate, then it propagates. But if you want to keep track of these like eigenstates, what you need to do, like you need to keep track of these two systems. Like you need to like continuously diagonalize and see like which eigenstate you are identifying, right? So the left part is coming from the standard flavor oscillation, oscillation picture, and the right diagram, as you see, this A, which is the the square root to GFNE, which I showed, like for the nu E, you get a extra matter potential. Okay. Somebody waiting. So, there will be two terms like this and this one. So now the thing is that you need to play around it, like which one can be dominant and which one can be subdominant. Whenever in the solar core, suppose say this matrix, this A is so high compared to this, you can neglect this. Like then you can see the like how nu E is completely changing due to these matter effects. Let me show you the some equation. So you see the survival probability when I wrote down in terms of the mass splitting and the angles. If you consider this matter potential, basically there will be a term which is this A factor, which is coming from the matter potential square root to GFNE, that will come into the picture. So with the normal oscillation, whatever your survival probability will be, that will be completely changed because of that. Because you have matter density is very high inside the say solar core, and when like it's going out, this matter density is getting down. So that's how like you can keep track of this matter effect also due to this fact. And here I'm showing that if this A term on the second matrix, which I showed, which describes the matter potential, if that is 0, then exactly this is the oscillation picture, standard oscillation picture. But if it is like your A is quite large, then it will completely change the whole scenario. Yeah, and these are quite popularly known as this. Iago probably have worked many times on these resonances. So in CERN, like basically you start with a new E as a new heavy eigenstate, but at some point, like basically due to this A, whenever it's getting lower, so it will change this Trevor transition will occur. This resonance will occur, and that will swap between the two states. These are popularly known as resonances. And this simplistic diagram, not going into detail. Maybe tomorrow I'll talk about it more detail. One thing here I want to mention, that one interesting thing here is that, like earlier I was mentioning, if you look at the high energy neutrinos, which are 10 MeVs, the electron survival probability, which we are finding around say 0.3, but if you go to lower energy after Borexino data, it's like 0.7 or so. And if you consider the MSW effect, like this MSW element prediction, you see that perfectly fits this data because of this MSW transition. And there are some other proposals also, which are called Maupin mass varying neutrino mechanism, as well as the MSW LMA NSI prediction. They also fits the data, but that's how like all these things I will discuss tomorrow more in detail, and talk about what is the early 20th century, this neutrino oscillation. Then if neutrino has oscillation, so how I can write down theory which can explain these neutrino masses and mixing. So tomorrow I'll discuss about that. I'll stop it here. So like with the solar neutrino
solutions
yeah.
post that in and when the mass varying neutrino.
Yeah, mass varying neutrino by Nelson and company, I think early 2000 or something. Yeah, these features are quite different. Yeah, but I'll stop it here. I'll discuss this other possibilities and this 20th century, what is the development and where we are now, and talk about the detail of the neutrino mass models.
Thanks, Sudip, for this. Any questions? audience.
So why is the matter effect very small in case of cosmic neutron? Neutron coming from the downside. So this the matter effect is small except in the cosmic neutron.
Yeah, but
But the downside it remains in the core.
like,
Passes through also the core.
yeah, but the small distance it is traveling from the upside. And from the downside, it is traveling long distance, you get enough chance to oscillate because it depends on the length also, right?
Yeah, oscillation is
Yeah, so it gets chance to oscillate, so that's why you are getting this efficient. Whereas you are, whatever you are getting there, like it's travels very short distance, so.
for the solar neutron also it has a lot of, I mean, distance is very huge, right? So oscillation,
No, from the sun to here, this is kind of vacuum oscillation, right? There is no matter. Like, if you can think about solar matter effect or like in Earth also matter effect could be there. But in between, when it travels, like it's completely vacuum.
no, I'm saying that for solar cases.
Yeah.
The distance is more, so the oscillation effect should be, and the matter.
Yeah, in Earth, I think matter effect is negligible.
Yeah, yeah, our loading distance is E by the sun and the earth, but the matter effects. So the matter effects affects the neutrino system in such a way that the neutrinos produce as an eigenstate, as a matter eigenstate. So when it reaches the value, it's still one eigenstate, it's not a superposition of eigenstates. So although the distance is large, it will possible.
So I think it shows some flaws in that when they exit the sun, you go back, I don't know which.
For low energy neutrinos, you could yes, well,
Yeah, for example, this level 4 crossing diagram.
Yeah.
I think the level crossing diagram, is that because
No, that's inside the sun.
that's inside the sun.
Total that part will show a spectrum of solar neutrinos.
Okay.
Like this thing is from the energy, like that show the transmission.
Oh, I see. I see. You are talking about this electron survival probability as well. Okay, okay, I got it.
Yeah, this one.
This one.
So the high energy part, it doesn't oscillate. Just the matter effect, which is very relevant. But in the low energy part, it's oscillating. And that is the average oscillations.
Yeah, so that actually I'll talk in detail tomorrow also. In the low energy, why you are getting almost like 0.7 and high energy, you are getting like the survival probability 0.3. And you need some transition due to that and how it can reach there.
I think one of the question maybe asking is is the matter effect not important for atmospheric neutrinos? Upgoing neutrinos. When they cross the whole Earth, do you have to take the out matter effect?
Yeah, for the atmospheric neutrino, I think it's not so important, right? So
Yeah,
It depends on energy, right?
yeah,
for outgoing neutrinos, right? So it's important.
Yeah,
For
but
ICQ,
if the
it's
higher
important,
energy,
yeah.
we have to compare. Yes,
for the
atmospheric.
high energy, it will be important. Yeah, that's true.
Yeah,
And the neutrino telescope.
because it increases the energy departure curve. More and more. More and more. Depending on the decision of the experiment, it also relevant, right? For example, is also have to take the matter check. No, but.
Question. Because I think we have to have a discussion,
Yeah.
anything that we discuss. Yeah, I was curious about this. You talk about these magnetic moment solutions.
Oh, yeah,
So,
that was very interesting. Yeah.
what was the, because you said it fit the data quite well.
Yeah.
When people realized this was.
This was realized when the Kamland, tomorrow I'll talk about it. So snow, first of all, snow see this all flux adding up to one. That refutes many explanations. Because if you say nu E oscillates to some sterile, it can explain the deficit, but it cannot explain the T flux sum that it will add up to one. So that's why snow result was quite important. But then it's got completely refuted this neutrino magnetic hypothesis when Kamland result comes. Kamland result comes like because you think about like you are writing 3 neutrino flavor, 3 anti-neutrino flavor. Okay, and then you are writing down evolution equation with the neutrino magnetic moment. It connects with neutrino to anti-neutrino.
Yeah.
And that will have different expectation, whereas Kamland is seeing between different flavor oscillation. That's the first place where you saw the real oscillation pictures. So after Kamland result, actually, the neutrino magnetic moment hypothesis will come out. Yeah. So until then, like even if snow data, you can talking to Evgeny also like after snow data also, because you see snow was not sensitive, I think, to neutrino anti-neutrino.
So that we cannot tell.
Yeah, you cannot tell much. And also if you say with the solar metallicity or something, you can explain this kind of transition and so on. But the Kamland is the experiment which yeah, completely disfavors this scenario. Yeah, but after snow result, all other hypotheses are ruled out. Then still these two hypotheses are there, and then the Kamland's result completely ruled out this magnetic.
Topics that will be very.
Yeah.
I'm not sure we're going to discuss this in the next classes, but you mentioned briefly about the role of NSI explaining the solar neutrino problem.
Yeah, that's all the first proposal by Wolfenstein actually.
Okay.
Even if that was the first proposal of this, how to write down matter potential and everything like this, they're talking, write down this neutral current NSI like 4 Fermi type of interaction. From any interaction, you can Fourier transform and get down these forms of the neutral current interaction. And that was his proposal, that if you have charged like different flavor NSI, basically you can explain the deficit. But there, Mr. Wolfenstein wrote down explicitly all these like matter potential and all these details. But he never realizes in this standard 3 neutrino picture. So then Alexei and Mikhail, they do in the standard 3 neutrinos pictures also you can explain without going for new interaction, just with standard interaction.
If I'm not mistaken, that was that proposal that you can gave also, right? Wolfenstein.
Yeah, Wolfenstein just like you can integrate out. Suppose there are some heavy mediator, you do not need to consider any variables also.
Okay.
You can just write down that interaction and then you can see how, because if you have the A term I showed in 1, entry, it can appear in any other entry depending on the NSI you are writing, which 2 neutrinos you are, like there are 2 neutrinos and 2 like matters. So 2 neutrinos flavor can be different depending on which flavors you are writing down with these interactions. Can populate different entries. So then if matter density high, so then you need to take into account that patterns. That was the Wolfenstein idea. But then Mikhail and Smirnov say that you don't need to go to like new interactions and so on, just if you consider the standard interactions, that itself explains these things very well. Yeah, and also this nicely fits this in a, like the electron survival probability transition. So
There's a question from the Zoom.
Yeah.
From Radha Krishna. He said, are the neutrinos produced in laser jets subject to matter effects, or can they be treated as free neutrinos?
These are very complicated questions actually, like,
Sorry.
like in lasers and so on, whether you can look for matter effect. So it depends on many facts. Even if me and Iago, we wrote one paper on that, like from Compton thick AGNs,
Yeah, laser.
laser and other places, like whether we need to consider these matter effects or not. That's what is question, like in other places, not only. Actually, yeah,
He actually proposed that it's possible. To
Yeah.
market that.
yeah, exactly.
I thought your proposal is with magnetic moment.
No, that's a different paper. So we are saying that you can have some, say, Compton thick AGNs. Compton thick AGN means where matter density is quite high. So, okay, you get information from two elementary particles, photons and neutrinos. That is coming from outside. So imagine that photons are not coming out. It can happen also. If you have some high density, say like this, you have huge matter density where these gammas are not escaping out. So these are called Compton thick AGN. So then you will have no observation of this type of AGNs in telescopes, suppose say. But still neutrinos can come out. But since the matter density is too high, these neutrinos can go through some flavor transition. And that's what we discussed in the paper, that this can be one way of discovering Compton thick AGN, because in the astrophysics community, this is a quite important problem, how to discover this type of Compton thick AGN. Because if you do not have X-ray, gamma ray, how I can interpret? Although there is some kind of catalog where you can find different kind of AGNs which has like very high density. So yeah, we show some example, but of course, these are kind of under some assumptions, like what density you require to get this matter effect and so on. Yeah, so it's possible, but yeah.
You mean the idea is if you have a very high energy density and then the X-ray can escape,
Yeah.
but then how do you know it's
Yeah, but
Yes,
that's the thing we are discussing. So but the neutrino will escape. But if neutrino without matter effects, if it comes, it's a standard vacuum oscillation, right? And you know what should be this, these are popularly called flavor ratio triangles. If you start with defined, so say PP or P gamma interactions, or say from the muon decay, so muon damped, like you have this like flavor ratio, you know, when you are starting.
Right.
And then you know that this expectation will be what when it reach Earth, if you have some rough estimation about the distance. But if this flavor ratio triangle completely shifted, okay, then you can say something about that matter effects happens. Like that can be one way you say that. Of course, you can say that there could be some new interactions which can lead to this type of flavor ratio triangles also can be shifted. Then you need to look for energy dependent variables and other things, like in solar neutrino. How do you know this MSW effects is giving the best solution? Looking at this plot particularly. When you go to lower energy neutrinos, PP neutrinos, you have a different survival probability. And when you are going for, say, boron neutrinos or like high energy neutrinos, you have a different survival probability. And it's a completely dependent on the energy. And same thing can happen also in those cases. So then this is a different way of looking at it. So it can happen there also.
One thing that, so all the sources that ICTP have seen, of neutrinos, they are not significant neutrinos. They are only significant if you include, because you already know they exist on photons and solution. But these sources, they are not able to account for most of the flux. So probably there is a possibility that the most of the flux of neutrinos are neutron sources that are opaquing photons.
Right, yeah.
So it would be a scenario in which you have these control peak sources, and the neutrinos coming from there would be undergoing matter.
So you expect some shift, there is a flavor ratio.
Yeah.
Yeah.
Yes.
There'll be only like strong magnetic fields instead of matter, like high dense matter, but just a strong magnetic field that reflects the photon, so they don't reach it.
Strong magnetic field.
Yeah, I don't know. It's just like, because the thing is that you see the neutrinos, but you don't see the light, right?
Yeah.
So you're seeing that it's probably because the medium is opaque. Will there be like another source that just makes your photons to shift along the path, so you don't see them in the straight line you should see? So instead of matter, you have just a strong magnetic field, I don't know.
You like be expected like.
No, yeah, no. I'm just thinking if there is anything else but matter.
I'm like getting into
Yeah.
each have a very, very.
Yeah, I know that's true.
I think matter is between the
Yeah.
ones first,
Yeah.
and also, yeah.
Like in neutron star merger, suppose you can have some large magnetic field there.
So, yeah, this is another kind of evidence that because insects, so when the neutrinos are produced in these astrophysical environments, in the source of photons, because they bind the charged ions to keep it neutrinos, and the neutral ions to keep it photon. So you expect neutrinos and photons to have kind of the same order of magnitude energy. And as we see the neutrinos, but the gamma ray telescopes are not seeing the photons. So the hypothesis that the photons are losing energy along the way, and they are going to some lower energy part. And that is another kind of direct evidence for these
object.
kind of big problem. Yeah,
There was this also that result from ICTP that they're more relating anomalies with the network neutrinos being less position.
here is your.
I think that was most correlation or small correlations like that.
I don't know.
And this last ICTP part.
Is it based on regular exchange?
Yeah.
Yeah, they are looking for this Lorentz violation and so on, because you have a standard expectation between neutrino, how much it will take time, and photon, how much it will take time. Yeah, they are looking for that also. That this time gap between, because your standard expectation is neutrino comes out earlier. And photons, because it goes through many interactions, so typically you can compute this time interval when both can come out. So looking at that, they are testing this Lorentz violations and other things. You know.
Another question. Is it theoretically correct to assign a particular temperature to a neutrino based on their energy? Sorry, can you assign the temperature to the neutrino based on their energy?
I don't understand.
Yes, you need a thermalized system. But I'm not sure. Yeah, maybe you can clarify your question. You mean like neutrinos from some certain source? Because to define temperature, you need like a thermalized system.
Yeah,
Understanding. So not sure. Okay, so it meant he or she, I'm not sure, but it meant in the sense of using the relation E equal Boltzmann constant multiplied by temperature. And you can say, okay, neutrino emits energy, so they have such a temperature. What?
That's true for, radical. And it's purely for, thermal distribution, in external turbine. You can assign a temperature.
That is true. They were thermalized before. Then, yeah, because distribution can assign a temperature to describe that. Yeah, but in general, I guess that maybe it's not very useful. Right? A beam of neutrino is certain energy. That's not a.
I think some people do consider this neutrino force. I don't know the
Neutrino force.
yeah, like neutrino, four neutrino forces, and there this thermal field theory approximation. People are working.
I think C1 was C1 Fisher. I think the visiting professor in medicine. He has some neutrino force.
Okay, yeah. So
Then I'm not sure whether it's neutrino force.
yeah, there they assign some temperature, so that I know this.
But this is because the background neutrino, we assume they have some distribution of the baselines.
Even if I recently had a talk like where they're saying like this type of thermal field theory approximation you can do with standard QFT with matter effect, and both gives the same prescription, interestingly. So for the this neutrino force calculation is these are now people are working on it. These are very old topics. So you need to generally, if you try to these things, what probably you are asking, like you do the thermal field theory treatment. There are some other papers which show that you can do this standard QFT with matter effect, and you are achieving the same results basically. Like instead of like different way of looking at it.
In what's a QFT? In QFT, the thermal field theory is a QFT, but then the other approach is
Like considering matter effect, like you don't need to really go to this thermal.
like an oscillation.
Yeah,
and
yeah,
method.
For neutrinos particularly.
I think they call finite basic.
Yeah, finiteness.
You were talking about this magnetic field. Maybe magnetic field can be constant. And if you have some particle,
I don't remember exactly, but I saw some Minicourse using times. I don't know that's. I don't remember.
Yes, maybe you can also request some topics.
Yeah, you can
Discuss.
suggest some topic because it can be very long also. So this because I recently given Heidelberg, so it was 15 hours lecture. So 15 hours for 5 days. But since it is 3 days, if you have some favorite topics which you need to learn, or you want to hear, like the first day is more like more information. I just pedagogically just showing that when, where, what happens. So if you want to learn, suppose a model building, I'll for sure do like the how to write down tree-level seesaw models and radiative mechanism, how you can compute these things. Intuitively, there are two approaches you can do, either do topologically, like from the graphs, and also you can do with the operator-based approach. So all this detail probably I'm targeting to start from tomorrow. I'll give. So yeah, I'll teach those skills so that you can at least learn, even if you're not doing model building, so that you can have some picture what actually people are thinking, because sometimes when they look model, it's you can have infinite possibility. I'll tell you like these are very finite possibility. It's not like infinite possibility. If you are going for infinite possibility, why those are not interesting and how you can discriminate from the finite scenario. So I'll talk about all these details maybe next. But if you have some other topics also, I can try to tell.
Just send an email.
Sorry.
No, I send an email.
Yeah, you can send email also.
Whole weekend, the thing.
Yeah.
I think so. Are there just neutrino properties?
Yes, I will talk about it, how much I will get time, but anyways, in Sao Paulo, I'll give seminar so on that. So there, I think more detailed technical way I'll discuss this. Yeah.
So
Yeah.
give me our seminar is when it was to be
Friday.
this Friday,
Yeah.
tomorrow.
No, next Friday.
Oh, next Friday.
So my idea is that neutrino, when people say neutrino non-standard interaction, there I will discuss about neutrinos, other interaction, also photons interaction.
Okay.
So there it includes all new interactions. So I'm just not saying what in community called neutrino non-standard interaction. I'm saying neutrino is any new interaction. It can be with photon and how it can develop, or with some new mediator or something. I'm targeting that to cover in third lecture. On top of the standard interaction, how look at that, you can say something.
Yes, there's no more question on the line.
So now these lines you had something about the anomalies.
Sorry?
Yeah, the current anomalies.
Yeah.
I want to discuss.
Yeah, I'll discuss, but how much I'll get time, I don't know. Like, because these are also like, you see, I come up to like our century. So now I will discuss even if some of the problem exists till now, like which is 20 years old and so on. So to give you the overview, what are the problem exist in the, so I'll talk about last 20 years, what are the things are there exist. And then immediately I'll talk about detail.
The chat, I think, yeah. I think he or she mentioned that yeah, he missed the last answer. So I think it's the question about temperature. Yeah, maybe you can clarify. I'm not sure how what's the content is.
So, yeah, actually, I do not understand completely,
Yeah, I
like,
can.
what exactly.
Yeah, this is just a question. Yes, maybe it's just what's the use or is that useful to define temperature?
Yeah, and honestly speaking, I don't have a good answer, but if I say like for this background and so on, in those kind of cases, it is for. But other cases, but
Yeah, because if you need to know how the phase space is between the neutrinos, then that'll be useful. Okay, yeah, I hope that we got the questions. Yeah, I think you can, yeah, and it gives that if people have more questions, you can stay.
Yeah.
Just. Thanks Sudip again for this lecture.
Yeah.